Good day, students. Have you ever asked yourself, how does the sun's energy, which seems so distant, end up powering everything from a blade of grass to a roaring tiger? The answer lies in the flow of energy through ecosystems, and this flow follows the laws of thermodynamics. Energy enters through sunlight, gets captured by plants, and then moves through consumers and decomposers. At every step, it transforms but never disappears. This is where physics meets ecology. Let's start with the first law. It tells us energy can neither be created nor destroyed, it only changes form. In ecosystems, plants take radiant energy from the sun and convert it into chemical energy during photosynthesis. Herbivores eat the plants, carnivores eat the herbivores, but the total energy of the system remains the same, only changing forms. We can represent this with the equation delta U equals Q minus W, where delta U is the change in internal energy, Q is the heat added, and W is the work done. So, nature is never losing energy, it is simply repackaging it in different forms. Now comes the second law, and this one is key for ecosystems. It says every energy transfer increases entropy or disorder. That's why only about 10% of the energy stored in one trophic level makes it to the next. The rest is lost as heat to the environment. We can measure this efficiency using the formula efficiency equals energy at the next level divided by energy at the previous level multiplied by 100. This is why food chains are short. Energy loss makes it impossible to sustain too many steps. To visualize this, think of an ecological pyramid. At the base, producers hold the maximum energy, while at the top, predators hold the least. The first law is visible here, energy is conserved overall, but as the second law reminds us, its quality declines as it moves upward, with most of it dissipating as heat. This is why energy pyramids are always upright. You will never see an inverted one because energy degrades as it flows. Let's connect this to real life. In agriculture, shorter food chains, like plants directly consumed by humans, are more energy efficient. Compare this to plants cow-human. The second chain loses far more energy as heat. Similarly, fossil fuel usage mirrors the inefficiency of natural systems. Vast energy is wasted as heat in combustion. Even in our diets and farming choices, we are following the rules of thermodynamics, whether we realize it or not. Let's work out a quick example. Suppose a plant captures 20,000 joules of solar energy. Only 10% passes on at each trophic level. Using the formula, energy at nth level equals initial energy multiplied by 0.1 to the power n for the secondary consumer, n equals 2. So energy equals 20,000 times 0.1 squared. That equals 200 joules. So, out of 20,000 joules available at the start, only 200 joules make it to the secondary consumer. This huge reduction is exactly what the second law predicts. Let's summarize. The first law tells us energy is conserved. It keeps changing from sunlight to chemical to kinetic forms. The second law tells us energy degrades with each transfer, increasing entropy and leaving less usable energy. These laws explain why energy flow is unidirectional, why food chains are short, and why energy pyramids are always upright. In short, thermodynamics sets the rules for life's energy economy. Every bite of food, every breath of air is a living demonstration of these laws. I hope this session gave you clarity on how physics underpins the survival of ecosystems. See you in the next class with another exciting concept in heat and energy.